Okay, so we will start with section 1.7 today. Oh, it's beautiful. We're going to solve absolute value equations. And absolute value inequalities. Absolute value equations and inequalities. Remember, absolute values are when we have those bars around them, those straight bars, those are absolute value bars. So let's talk about what is an absolute value. An absolute value is a distance a number is from 0 on a number line. So absolute value is a distance a number is from 0 on a number line. So if an absolute value is a distance, can an absolute value ever be negative? If I get in my car and I drive, do I ever drive a negative distance? No. Okay? Anything that's a distance cannot be negative. So therefore, an absolute value of something can never be negative. So say I want the absolute value of 4. That would be 4. Because it's 4 spaces away from 0 on a number line. If I want the absolute value of negative 4, the answer is 4 because it's 4 whole spaces away from 0 on a number line. Okay? So first we're going to solve absolute value equations. And then later we will do inequality. So example A. As simple as it can be. The absolute value of x equals 5. So when you're solving something like the absolute value of x equals 5, you're saying the absolute value of what number is 5? So you're saying what number has a distance of 5 from 0 on a number line? How many numbers have a distance of 5 on a number line? 2 numbers. What are those 2 numbers? Yeah, so x equals 5 and x equals negative 5 are your 2 answers. So if you just have the absolute value of x equals a number, the answer will be the positive and the negative value of that number. Because both the positive and the negative have the same distance from 0 on a number line. Okay, so let's make it a little bit more difficult. Let's say the absolute value of x minus 5 equals 7. The absolute value of x minus 5 equals 7. Now, we don't know what x is. Okay? We don't know what x is yet, but we're going to solve this equation. So, if this is the absolute value of something right here in these bars, it could be 7. That gets me that number. Or what else could have an absolute value? It could also have an absolute value of negative 7. Right? The absolute value of negative 7 equals 7. So what's inside the bars has an absolute value of 7. So positive 7 has an absolute value of 7. And negative 7 has an absolute value of 7. So what we do to solve it, when we have a little bit more stuff going on, is we make 2 equations. X minus 5 equals 7, just like it originally says without the bars. And then we also can say x minus 5 could equal negative 7. So when you have the absolute value equal to a number, you set it equal to the positive number that it already is and the negative number. And when you do that, you leave off the bars. And so you're going to get 2 answers. Okay? Every absolute value equation is going to have 2 answers. So this is really simple equations. We're going to add 5, and x equals what? And then we're going to add 5 over here, and x equals what? Negative 2. Those are my two answers. Make sense? It's easy. It's easy. So let's make them a little bit more complicated. Absolute value of 5x minus 10 equals 45. So how do we work this out, do you think? How do we do it last time? Well, we make two different problems, right? For the first problem, we say 5x minus 10 equals what? 45, just like it does without the bars. And then, what's the other option I have? 5x minus 10 equals what also? Good, negative 45. So the first one is exactly like it says without the bars. The second one, you make it equal to the negative value of that number. And then you just solve the two equations. So we're going to add 10 over here. 5x equals 55. Divide by 5, and x equals what? 11. And then we have 10 over here. 5x equals negative 35. Divided by 5, and x equals negative 7. So those are my two numbers that'll work. And let's just check that out for a second and see why it works. If I put 11 in for x, 5 times 11 is 55. 55 minus 10 is 45. Is the absolute value of 45 equal to 45? Yes. Well, let's try it with negative 7. 5 times negative 7 is negative 35. Minus 10 is negative 45. Is the absolute value of negative 45 equal to positive 45? Yes. So that's why it works. Is this difficult? Okay. I'm going to get you guys to try a couple then. Page 3. If I can get the page numbers right. All right, y'all try this one. Absolute value of, let's just do this one. Y'all try that one. And when you got your two answers, you can go ahead and check the partner. All right, what's the first equation you write down? Somebody tell me the first equation they wrote down. Good. X plus 2 equals 10, and what's the second one? Very good. And then you subtract 2, and you get x equals what? It's one answer, and then you subtract 2 over here. That's supposed to be 10, negative 10. I don't know why I put negative 2. My bad. And then I subtract 2 over there, and I get x equals what? Negative 12. Raise your hand if you got 8 and negative 12. Any questions about those? So those are absolute value equations. And y'all, equations have equal signs, right? So next, we're going to do absolute value inequalities. What's an inequality? We talked about them today. What symbols do inequalities have? They don't have equal signs. What do they have? Less than or equal to, greater than or equal to are all of our inequalities, right? So when we do absolute value inequalities, and we also talked about compound inequalities yesterday, and we talked about ands and ors, right? So something I want y'all to remember that will help you out here is the phrase land of goer. I know that sounds weird. Land of goer. If you had me for Algebra 1, you might remember this phrase, okay? So, what the phrase land of goer helps us do when we see a less than or a less than or equal to in our absolute value inequality, it's going to be an and problem. And if we see a greater than or a greater than or equal to, it's going to be an or problem. So and goes with the L to make the word land, and or goes with the G to make the word goer. So land of goer, less thans are ands, greater thans are ors. Okay? So, let's say I write this one. What example is this? D? Okay. So example D here. Say I have this example. Absolute value of 4x plus 5 is greater than 13. Okay? So what symbol is this right here? Greater than, and I just told you a greater than is what kind of problem? It's an or, right? G goes with or to make the word goer. So greater thans are or. So it's an or problem. Now to set up an or, here's what you're going to do. Oops. What you're going to do is you're going to leave off the bars and copy the problem inside the bars. And at the end of the bars, you're going to change it to less than a negative. Change it to less than and make it this one negative. And then you're going to write the or. And your second inequality you're going to write is going to be exactly like the original one says without the bars. When we did shading yesterday, which way did ors shade? Yeah, they shade in opposite directions. Okay, so that might help you remember when we have an or, if it's greater than or equal to, it's an or. So also our inequalities need to be in opposite directions. So you want to be less than the negative number and go to the left, or greater than the positive number. So if you're an or, you're going to be less than the negative number or greater than the positive number. And the left side of the inequality is going to be exactly what was in the bar. All right, then you're going to solve two different problems, just like we did yesterday. So for this left-hand side, you're going to subtract 5 on both sides and get 4x is less than negative 18. I'm going to divide by 4, and that'll reduce to x is less than negative 9 over 2. And if you don't like that improper and you want it mixed, it's the same thing as negative 4.5, right? And then just like yesterday, we need to keep or in our answer if we have an or problem. And then we solve the other one like it's a whole separate different problem. Okay, so over here, we'll come over here and subtract 5 on both sides and get 4x is greater than 8. Divide by 4, and we'll have x is greater than 2. So this is our solution. if our directions say to graph the inequality or graph the solution, -4.5 is between what two numbers? Yeah, so if you just want to just keep it whole numbers on your number line, that is okay. And we said or shade where? Opposite directions. So -4.5 is right here between the -4 and the -5. Does it get an open circle or a closed circle? Does it say or equal to? No, so it's open. Shade left. And 2 gets an open circle and it shades right. So let's do one more OR problem. When do you have an OR? When you have what symbol at the beginning? Greater than or equal to. Very good. So let's do this one. Absolute value of 2x minus 7 is greater than or equal to 1. See, on your homework today, on your assignment, it's going to mix all the greater thans and less thans all up. So you've got to be able to look at it and say, yes, it's an or yes, it's an and. Okay? You've got to be able to look at it and tell. So I guess I should have mixed up our examples, but I did not. I read. So it's a greater than or equal to, so that makes it an or problem. So we take what's inside the bar, and we make it the first one less than. And since this was less than or equal to, I need to keep that or equal to, okay? So less than or equal to the negative number on the outside. Or the second one, we keep it exactly the same as it originally says without the bars. So you're going to have less than or equal to the negative or greater than or equal to the positive. And then we solve them for x. So I'm going to add 7. 2x is less than or equal to 6. Divide by 2. X is less than or equal to 3. I'm going to go ahead and put or with my answer so I don't forget it. Add 7 over here. 2x is greater than or equal to 8. Divide by 2. X is greater than or equal to positive 4. Any questions on that part? And what about my graph of my number line? What's going to happen? What's it going to look like? Oh, these are positive numbers. Why am I making it so big? Sorry. 1, 2, 3, 4, 5. Where do I shade ors? Opposite direction. So 3, does it get an open circle or a closed circle? Closed. Shade left. What about 4? Open or closed for 4? Closed also. So where are, which numbers are not included in these solutions? The numbers between 3 and 4, right? Now what kind of numbers are between 3 and 4? Are there any numbers between 3 and 4? Yeah, there's a lot of fractions and decimals between 3 and 4, right? Like 3.5, 3 1/4. There's infinitely many decimals between them. Can y'all try an or for me, please? I'll make it small. Absolute value of x plus 4 is greater than or equal to 6. Y'all try that one. The setup is the hardest part at the very beginning. On that number line, if you want to go by tens, you can, because these are kind of spread out, I think. All right, so most of y'all are finished. All right, is this one an and or an or problem? Or, because that's all we've worked so far, but how do we know it's an or? If this was mixed all in together with our homework, how do we know this is an or? Because it says greater than or equal to. So we know if it's greater than or equal to, it has to be an or. So how did you set up your two inequalities then? What's the first one say? X plus 4 is what? Less than or equal to negative 6. Or x plus 4 is what? Greater than or equal to positive. Okay, so every time you do an or, you split them up like this. Is everybody okay with the setup? Okay. Then you solve them. And we get x is less than or equal to negative 10. Or, subtract 4 over here, x is greater than or equal to 2. So I'm going to graph these, and they were made in different directions. And I told you if they are far apart like this, you can go by 2s or 5s or whatever you need to do. Twos make sense for this one. And these both get closed circles, don't we? And we're going to shade these in opposite directions. Double O, or shade opposite. So raise your hand if you got that correct and your number line looks something like mine. Any questions? Yeah, go ahead. It's called You Have Got to Have a High School Diploma. So state of Tennessee says you got to do it. I'm saying I agree with you. And that's all I'll say about that. No, that's good stuff. All right. So the last example we had was which one? E. So let's do F. Now let's do an and inequality. So if greater thans have or inequalities, then less thans will be ands, right? And I actually think that ands are a little bit easier than ors because it seems like there's less work to do. So when we have a less than or less than or equal to, it's going to be an and problem. And that's where that phrase land of Gore comes in to help us out a little bit. Less thans are ands. So if you have an and, what you're going to do is you're going to take that number on the outside and you're going to make it negative. And you're going to set it up like a compound inequality. So compound inequalities all have less thans. The variable went in the center, just like yesterday. So we're going to put whatever this symbol is right here. It should be a less than or equal to make an and. And if it's less than, we're going to use less thans. So we're going to say less than, whatever's in the bars go in the middle. And then less than 10. And then it looks like a problem like we did yesterday. So all you have to do is stick a negative on the left side, a positive on the right side of whatever that number is, and then whatever's in the bar goes in the middle, and whatever symbol you have is your two symbols when it's an and. So how do we solve this for x in the middle? Add 8 everywhere. And we have -2 is less than x is less than 18. Now that one's going to be kind of fun to graph because those numbers are really far apart. But we can go by 2's. Now where do and shade? Yeah, they shade toward each other. They shade together. So I'm going to do it like this. I'm going to go by 2's. 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So anytime they're far apart, see what number you can go by to make sense to your problem. And these are both less than's, not less than or equal to. So do they get open or closed circles? Open. And 18. And where do we shade? In the middle. And shades together. Or shade opposite. Can I do that? Let's do one more and. Absolute value of 2x minus 3 is less than or equal to 5. Is this an and or an or? How do you know if it's an and or an or? We don't know. Miss Isabel just tells us. Land of Gore, right? So which one is it if it's a less than or equal to? It's an and, right? Less thans are ands, greater thans are ors. That includes or equal to's. So, y'all remember, what did we do last time? What do we take that number on the outside and what do we put on the far left? Negative, right? -5. And we copy that symbol. Less than or equal to 2x minus 3. Less than or equal to +5. And we can solve it all together. When we get the x in the middle completely by itself. So we can add 3 everywhere. So I'm getting -2 is less than or equal to 2x is less than or equal to 8. Divide by 2 everywhere. And then I'm getting -1 is less than or equal to x is less than or equal to 4. And these aren't too far apart, so I'm just going to use single digits here, or single numbers. -2, -1, 0, 1, 2, 3, 4, 5. Do these get open circles or closed circles? Closed, because they say or equal to. And where do I shade them? Yeah, shade together. And means together. Can y'all do those on your own, you think? Think we'll be good? Or y'all want to know something exciting? No, I'm going to skip that as well. This is the end of chapter 1. Yay! Okay. So guess what we're going to do now? We're going to start chapter 2. But we're not going to do much. Now, chapter 2 is really a graphing chapter. So we're going to save our graphing until tomorrow. We're going to talk about slope and graphing with slope-intercept form tomorrow, if we're here. If we're not here, whatever day we come back, that's what we'll do. So if you don't have graph paper yet, you need to find you some. I'll have a few sheets you can borrow, but I don't have enough for every one of y'all every single day. So make sure you provide yourself with some because you'll need it a lot in this class when we start graphing a lot of things. So let's talk about things with graphs today. And we're not going to exactly be graphing, but we're going to talk a lot about graphs and functions. So section 2.1, we're going to talk about representing relations and functions. Now, a relation is just a set of ordered pairs. Okay, and we'll talk about functions a little bit more in a little bit. But a relation is a set of ordered pairs. Now, ordered pairs, another word for those are what? Points, right? Or coordinates, all right? They have an X and a Y. They have parentheses and a comma between them, right? We've seen them before. Probably every math class we've had since 7th grade. Maybe even 6th grade or before, okay? So also when we have relations, we have a domain of a relation. Those are our sets of input values. Also known as our X values. Okay? So our X values are our domain. And what else do we have besides domains? What's the other one? What goes with domain? Do we know? We ever heard of domain before? I know we have. So the other word that goes with domain is range. And that is the set of our output values. So if domain is our X values, what do you think our range is? The Y values. Very good. So domain is the X values, our range is our Y values. If you get them mixed up, it's in alphabetical order. X comes before Y, D comes before R. Right? So if you get them mixed up, that's one way you can remember. All right, so let's start with a relation, which is a set of ordered pairs. Let's say we have this set. All right, so that is a relation. A relation is just a set of ordered pairs. Now, I have listed the ordered pairs. It's just a list of ordered pairs. That's one way to write a relation. Another way is in a table. Now, sometimes we see tables written horizontally, okay? I prefer to have them vertically. But that's when you have a list of your X's and a list of your Y's. And they are beside the number they correspond with. So for the point -2, 3, which one is the X, which one's the Y? Which one's the X, which one's the Y? Yeah, they're in order, right? Ordered pairs are always in alphabetical order, X and Y. So the X value is -2. The Y value is 3. So to finish out my table, the next point, -1, 1. -1 is the X, 1 is the Y. In the next ordered pair, 1, 3. 1 is the X, 3 is the Y. The next one, 2 is the X, -2 is the Y. And then lastly, 3 is the X, 1 is the Y. So sometimes we see tables written vertically like this. This is the way I prefer them. Or sometimes the book likes to do them horizontally. I really don't like them that way. Sometimes if I see them that way, I turn around and make them vertical. But whatever makes sense to you. We also can see them sometimes in a mapping. Now, you don't see me do this often. But it happens and it'll occur in your book. So I want you to see it. When I do the mapping, they have your list of inputs on the left and your outputs on the right. Now, when you say inputs and outputs, I want you to think inputs are X's, outputs are Y's. And again, those are also alphabetical. So for this relation, your inputs are all your X's. And you have like 2 ovals, and I know mine are horrifically ugly. So I have 3. Actually, what you do is you put them in numeric order. So lowest to highest, -2, 1, 3 are my only different y's, aren't they? And so what they do, you put them in order from numeric order, top to bottom. And then -2, 3, the x value -2 maps to a 3. So you draw an arrow to what it goes to. That's why it's called a mapping. So -1 goes to what y value? What's the point -1, 1? So the -1 goes to the 1 y value. So +1 goes to what number? 3. 2 goes to what number? -2. And 3 goes to what number? 1. Now that's a big old mess, isn't it? Looks like a big mess because they share so many of the y values. Okay? And the last thing that we're going to do for this relation is we're going to list its domain and range. Now in your notes, we just have it written up there. What is a domain? What's a domain? The x values, right? And you just put your x values in order from least to greatest. And since we have them in a table, that's a nice, neat way to copy them. And make sure they're least to greatest. So the domain of this set is -2, -1, 1, 2, 3. So all my x's. Now the range is your list of y values. So what are my y values? Well, they're all these, aren't they? Except we want to put them in order from least to greatest. And also, when you write your range, you do not have to repeat them. So if it's something that's repeated, like the 1's repeated and the 3's repeated, you only have to show them once. So the lowest number in my range is -2. And then the next lowest number is a 1, and the next one is a 3. So when you do domain and range, you put them in order from least to greatest, and you do not have to repeat them. Okay. So the next thing we're going to talk about is we are going to learn to be able to tell whether a relation is a function. Tell whether a relation is a function. Okay. To tell whether a relation is a function or not, okay, a function, every input matches to its own output. I said that backwards. For every output, there's exactly one input, I think is how it's supposed to be said. But anyways, what you need to do is do not repeat your X's. So if a relation is a function, that means none of the x's are repeated. You can repeat your y's and still be a function, but you cannot repeat x values. So that relation we just talked about, are any of the x values repeated? A lot of the y's are repeated, right? But they're all different x's, aren't they? Okay, so that relation would be a function. Okay, so a function is when we do not repeat our x's. If they're all different x's, it's a function. So I'm going to show you some examples of some relations, and you guys are going to tell me if it's a function or not. And I'm going to give you some mappings. I'm going to get some more space. Say I have this mapping. Now, which one cannot repeat? Yeah, the inputs, okay? The x's can't repeat, right? Can the y's repeat? Yes. Do I have any x's repeating? No. Every one of those x's all have their own line going to the output box, right? So the x's are all different. So do you think this is a function or not a function? Is it a function or not a function? It is a function. Yes, it is a function. All the x's are different, so it's a function. All right. Here's another one. I can spell output. That'd be helpful. Function or not a function? Not. Why not? Well, that 1 right there is being used twice, isn't it? So the inputs are my x values, and that 1 is being used twice. So if any of the x's repeat, it's not a function. All right. What about graphs? Now, since back in junior high, you had something that told you whether or not was a graph was a function. Y'all remember what that was? Started with a V. Vertical line test. Raise your hand if you've heard of the vertical line test before, or VLT. Vertical line test will help you determine whether or not a graph is a function. So we don't have graph paper, so I'm just going to do some rough sketches. So let's say I have a parabola. We all know what parabolas look like from Algebra 1. Is that a function? Vertical line test is if I can drop a vertical line anywhere on that graph, and I'm only touching the graph one time. Now, a graph is not the x and y axis. The graph for this one will be what's in red, for instance, the parabola. Okay? So if I put a vertical line anywhere and it touches the graph twice, it is not a function. But everywhere I put vertical lines on this parabola, I'm only touching that parabola one time. Right? So is that parabola a function? Yes, it's a function. Okay? Let's say I take that parabola. No, you're fine. Hang on a second. Let me pause my recording. I don't want to split up. All right, I'm blue, so good. So if I take that parabola and I turn it on its side, now is it a function? No, why not? Because there's multiple places, and it only has to be one place. But there's a lot of places where if I drop a vertical line, it's touching in two places. So that makes sense. Are we good with that? What about, we're going to talk about different polynomial functions this year, or this semester. What about if I have a curve like this? Function or not a function? It is a function. What about if I take that same function and make it go like this? Not a function, because I'm touching the vertical a lot of times. All right? Obviously, a circle is not a function. So I drop a vertical. And we also have absolute value graphs, which we'll talk about lots later, which is a V shape. Function or not a function? Yeah, it is a function. So, anyway, so there's some examples of those. And we are going to stop the video right now.